Okay, Highlanders, the day has finally come. Your last section of notes in Honors Pre-Calc, the last chance I have to teach you anything, and we go back to talking about lines and planes in space. So this is a two-part lesson. We're going to start by just talking about lines, and then we'll come in and show you how we get plane equations. So lines, right? Let me see if I can. One more shot at this here. All right, I guess that's as good as it gets. All right, lines. To have an equation of a line, what do you need? You need a point and a slope. Right? You need a point, you need a slope. Or 2 points. That's what you got to have. So the problem is that we can't just add a third variable and call it a line. If you remember back in chapter 7 when we were doing our systems of equations, and I told you that that the three variables, we did 3 by 3 systems, that those three variables created a plane equation. So really what we had was the intersection of 3 planes. When we intersected 2 of them, we got rid of z, and that left us a line of intersection. Then we intersected 2 of the other planes, and we got another line of intersection, and we intersected, etc. Right? But the x, y, z back then, I told you, was a plane equation, and that's what it is. Okay, so that's important to note. So if we're going to try to find the equation of a line in space, the only way we can do it is through parametric form. Right? So remember what parametric meant. It meant that we had a third variable, like a parameter, something that we were able to, back in chapter 6, we were able to eliminate parameter, 6, 10, chapter 10 maybe. Anyway, we were able to eliminate parameters or create parameters so that we could have x in terms of the parameter, y in terms of the parameter variable, but now we could also have z in terms of the parameter variable. So let me show you how this works. So let's say we're going to start with this. Okay, so we got some line in space. So I'm just going to kind of draw in my axes here. So here's x, here's y, and here's z. So we just got some line out here. So again, we have to know a point. So let's call that x1, y1, z1. And again, I'm subscripting the point because we know it. We know what that point is. And then I'm going to grab some, can't call it P, call it Q. Just another point on the line, can be anywhere, it doesn't matter. Okay? And I'll tell you why I need that other point in a minute. Now, because this is in space, I can't really measure the rise and the run because it's not on a plane, right? There's 3 dimensions, not 2. So how do you bring in the angle, and it gets all icky and complicated? So what we do instead is we have what is called a slope vector. So we have this vector that is what I like to call the slope vector. They'll call it the directional vector, but it's a vector that's going to be parallel to your line, right? And that has to be given as well, right? So in this case, we have a point in space, and we have what is called our slope vector. And we know that this has to be parallel to this line. So because they're parallel, they have the same slope, or they have the same direction, right? So that's how this works. So now this is point and slope. Okay? So what we're going to do is we're going to take and we're going to translate this. And this is where this point Q comes in, right? Doesn't matter where it is. Just put it on there. But now what we have is just, I'm going to grab this vector, right? Just that piece of the line there. And I'm going to translate it to the origin. So by doing that, remember we have to subtract. So the vector PQ becomes x minus x1, y minus y1. Remember when we translate to the origin, and I'm using the point as the initial point, the given point as the initial point, we subtract. Okay? And then this has to also be given, so I'm going to just say that. That's my slope vector. Okay, so v is my slope vector, and its coordinates are a, b, and c. And keep in mind, you will be given p, and you will be given v. And I'll show you an example in a minute. Okay? Now, here's what we know. This vector and this vector are parallel, which means they're scalars of each other. Remember in lesson 2, 3, 2, I think it was, we talked about two vectors in space that are scalars are parallel, right? And these have to be parallel because this line has to follow the same direction as this vector. So, because they're scalars, I know that x minus x1, y minus y1, and z minus z1 has to equal some scalar, and here comes our parameter, times my slope vector. Right? So whether this vector is bigger or smaller doesn't really matter. And so what does that mean? Because this right here is what they don't tell you in the book, and I think it's important. This is called a vector equation because we've equated two vectors. But I also know now that x minus x1 has to equal a times t, because that's the scalar, right? Y minus y1 has to equal b times t, and z minus z1 has to equal c times t. Or, solving for x, y, and z, x equals x sub 1 plus at, y equals y sub 1 plus bt, and z equals z sub 1 plus ct. And keep in mind, x, y, and z is your variable. This is the given point. That's the given slope vector. And each one of these cases looks like it's y equals mx plus b, which it kind of is. Right? So we can use this parametric form given any slope vector, given any starting point, and then we can draw the line in. Right? So this would be the format then of the parametric form of your line in space. Again, you will be given this, and you will be given A, B, and C, and then all you need to do is grab a t point. And it doesn't matter what the value of t is, you start plotting those points, guess what's going to happen? As you change the value of t, those points are going to line up right here. This right here is going to translate you to this point, because when t is 0, right, you're going to go x, y, z, right? Well, the x, I don't know, x, y, z, whatever, but it's going to take you to that point right there. That's what this does. So that takes you to the line, and this makes you follow the slope vector, and t is going to take you all the points along the line. Okay? So here's what an example of that would look like. Let's say you have point P. Here's your point, which might be 1, negative 3, 4. And your slope vector might be 1, let's go 4, 2, negative 1. Okay? So you want the equation of your line in parametric form containing that point parallel to that vector. So now do we need to go through and get a point through the whole process like I did here, get the variable, set up the vector equation, and so forth and so on? We're going to do that. No, you don't have to because you have the format already, but again, you would need to bring in, this is the process behind what we're doing. Some x, some other point on the line, translate using P as the initial point to get the vector. So this becomes x minus 1, y plus 3, z minus 4. And we know that this vector now because that's my slope vector, is parallel to v, which is 4 to negative 1, which means this vector is a scalar of that. So we bring in some scalar multiple. So x minus 1, y plus 3, z minus 4 has to equal some scalar. We use t because it's our parameter variable of choice. There's your vector equation, which means x minus 1 has to equal 4t, y plus 3 has to equal 2t, and z minus 4 has to equal negative 1t, or in its parametric form, x equals 1 plus 4t, y equals negative 3 plus 2t, and z equals 4 minus t. Right? So again, what do we see? There's my point, there's my vector, my final result. This is the process to take you here. I don't expect you guys to walk through that process every time, but I want you to understand why this works and why this represents the line. Again, this translates you to one of the points on the line, and these slopes here make you follow the slope vector so they're parallel. And if you want to find some points, just plug in a value for t. For example, if t is 0, we get 1, negative 3, 4, which was our given point. If t equals 1, we get 5. Negative 3 plus 2 is negative 1, and 4 minus 1 is 3. So there's another point, and all of these points are going to be on that line in space. Okay, if we take and we eliminate the parameter here, so basically what we're going to do is go to this, right, isolate the parameter, so we get x minus 1 equals 4t, we get y plus 3 equals 2t, and we get z minus 4 equals negative 1t. And then solving each of these for t, which is how we would eliminate it, t is equal to x minus 1 over 4, t is equal to y plus 3 over 2, t is equal to z minus 4 over negative 1. And since these are all equal to t, they are all equal to each other. That is called symmetric form. Not very useful in my mind, but all we're basically doing here is taking our parametric form of our line, eliminating the parameter to get some symmetric form. But that's what that is, and it's in the book, and you have to do it, so I just wanted you to see it. Again, not very helpful, very useful. Okay, so that is the first thing that we did. Remember, what happens if you're given a point and a slope? But again, like every single line in space is defined by any 2 points, right? We know from geometry that any 2 points determines a line. Therefore, what if I give you 2 points? How do we find the vector, or not, sorry, the parametric equation of the line in space? So, let's say A is at 1, 7, negative 6, and B is at 4, negative 1, 2. So there's 2 points in space. Find the equation. So keep in mind, and this would be in parametric form, if I did this in the plane, what would be the first thing? Like if you only had 2 ordered pairs, first thing you would do is find the slope, and then you would go to point slope. Well, here we need to find the slope vector. So the way to do that is to just translate, right? Because the segment that joins these 2 points is obviously parallel to your slope vector, which you need to find. So we do that by just translating this segment back to the origin. So we get 3, negative 8. Again, I'm just subtracting 8. So this can be used as your slope vector. Now, if we subtracted this way, these would all be opposite signs, in which case that would mean that the vector would be flipped 180, but still showing a proper direction, because again, it doesn't matter if the vector is doing this or it's doing this, right? Still going to have the same direction no matter what. So the order in which you subtract doesn't matter. I just happen to use A first because A came first. So now I have my slope vector, and I've got 2 points. So which point do I use? Well, when you were doing point slope, which point did you use? Answer, it doesn't matter. Makes no difference which points you use, they're both going to work. So I'm just going to skip the intermediate step here, jump right to x equals, and if I choose point A, 1, remember this is my slope vector, y equals 7 minus 8t, and z is equal to negative 6 plus 8t. Okay? Or, if I used point B, x would be 4 plus 3t, y equals negative 1 plus, or minus 8t, and z equals 2 plus 8t. Both work. Both represent the same line. Right? So, if I said here that t was 1, what would this give me? With t equal to 1, I would get 4, negative 1, 2. Point on the line. Right? Here, if I said t was negative 1, what do I get? 4 minus 3, negative 1 plus 8, and 2 minus 8. That point, right? So there are ways to make these obviously both work. In all cases, you're going to get the same equation. So again, if you don't have a slope vector, you're just given 2 points. You need to find that slope vector by using one of these 2 points as an initial point, translate it to the origin to get the slope vector in standard position, and then just pick one of the 2 points and put it in your parametric form. So that's how we deal with lines in space. We use the parametric form of them, and it allows us to, graph the line. It allows us to, we can find points by just picking whatever values we want for our parameter and going about our business. Okay, so that's the first part. Now, what about planes in space? Planes in space. Okay. Well, first of all, here's what we know. We know that if we calculate the cross product of 2 vectors, we're going to get another vector that is perpendicular to both of them. That's important here. Also, remember that any 3 non-collinear points form or determine a plane, right? So this is where we want to get to. I want to be able to give you 3 points in space and have you find the plane equation that contains them. But first, back to my point. So let's say I give you 2 vectors. Let's say vector u is u1, u2, u3, and v is v1, v2, v3. Okay, so when we cross those, we get a vector that is perpendicular to both of them. And just let me remind you what the cross product is. So u cross v is a vector. It's u2 v3 minus u3 v2, and then it's u3 v1 minus u1 v3, and then it's u1 v2 and u2 v1. Okay, so this, remember, perpendicular to both of those, right? And Also, this has another name. It's called the normal vector. And normal vectors are always perpendicular to the other two vectors. So these two vectors connected at the origin, okay, the normal vector is perpendicular to both u and v, right? So this would be considered u cross v, okay? So some other geometry, a lot of geometry in this chapter, but when you take two segments and you intersect them, and we know these are going to intersect because they are in standard position, and if they're not, you need to put them in standard position first, right? But they're going to intersect. So because they intersect, we know that their intersection is contained in a plane. You take any two lines, no matter which way they're going, and you cross them, right? You make them intersect, then there will be a plane that contains them, which means there's a plane that contains both u and v. Which also means is that this cross product vector, the normal vector, is going to be perpendicular to that plane as well because it passes through that point of intersection. All right? So anytime you calculate the cross product, in other words, you get the normal vector, that's just the name they gave it, you will get a vector that is perpendicular to the plane that contains the two vectors that you use to calculate the cross product. That's important. Okay. So, let's say I give you a normal vector. So the lowercase kind of script n. We'll say this is the normal vector. Okay. So A, B, and C represent the x, y, and z components, the terminal components of the normal vector, right? That's this guy right here. So we're going to call that A, B, and C. And then I give you P, which is some given point in the plane, just like we did with the line, right? So P is lying in the plane. So we have sort of this thing going on here, where you've got N, and then you got P. Okay, so now what we need to do is we need to get Q, which is any random point in the plane. So Q is going to be another point on the plane. It can be anywhere. So just, it doesn't really matter where Q is. So that creates this segment in the plane. So what are we going to do? We're going to take this segment, PQ, and we're going to translate it, because remember, if that's a normal vector, that's the origin. And this plane can be tilted any which way. Doesn't really matter. Right? We can move it around. Doesn't matter. Now, I'm going to take this, and just like I did with my line, and I'm going to translate so that this becomes a vector PQ. Alright? So, that looks like this. Again, I'm using my given point as my translation piece. So the vector for PQ becomes x minus x sub 1, y minus y sub 1, and z minus z sub 1. And here's the neat trick. What do we know about this vector and my normal vector? Because the normal vector is not a normal vector unless it's perpendicular to the plane. Therefore, it's perpendicular to every single line in that plane that passes through that point of intersection, which means it's also perpendicular to my vector, right? And if it's, these aren't very parallel, but I'm sorry about that. Anyway, so if it's perpendicular to my vector, if I got two vectors that are perpendicular, what does that mean? It means that the dot product is 0. I can hear you screaming it from here. So that means that PQ dot with my normal has to equal 0. So again, PQ is x minus x1 y minus y1, and z minus z1. And my normal vector, we said, was just a, b, and c. So when we calculate the dot product, we get a times x minus x1 plus, remember the dot product's a number, b times y minus y1 plus c times z minus z1. So doing a little algebra now, we got ax plus by plus cz. And don't forget, this a, this b, and this c are coming from your normal vector, right? That's what n is. Those are numbers. And p, right, the x1, y1, z1 is the point p, right? That'll be given to you. And those are numbers. So I'll show you, whoops, that's the point. I'll show you how that all works in a minute. So, what else do we have here? We have a negative ax1. We have a negative by1, and we have a negative cz1. So if you think back and remember what your plane equation was, what I told you, it was ax plus by plus cz plus d equals 0. X, y, and z are the variables in the plane equation. Look at what a, b, and c are. They're the coefficients of those x, y's, and z's. So without knowing it, this vector, a, b, c, is the normal vector. That's why it's so important, because it's a big part of your plane equation. And then all of this is your constant. So, if I give you the normal vector, let's say my normal vector is 1, 2, negative 4. And point P is, whatever, 6, 3, 1. You can write the plane equation because you already know this much. You know that that's A, right? So you have 1x plus 2y minus 4z plus d is equal to 0. Now, how do we find d? We can do this little product here, or there's a much quicker way. Because since p has to be in my plane, it has to be a solution to this equation. So if I just plug these into x, y, and z, right? So in other words, 1 times 6 plus 2 times 3 minus 4 times 1 plus d is equal to 0. So 6 plus 6 is 12, minus 4 is 8. So d has to be negative 8. And you have the equation of the plane. So critically important here. A, B, and C are the components of the normal vector. Alright. So that's if you're given the normal vector and a point on the plane, you can find the equation of that plane. Notice that, again, this is just like the 3x3 system equations that we talked about before. But you didn't know the significance of those coefficients. But now you do. Alright, so, again, big thing in geometry, right? Any 3 points determine a plane. So, that being said, I should be able to give you 3 points. Now I'm just going to grab a problem out of the book here. Let's do 28. 4, negative 1. Or we'll do 35, negative 1, 4. B is going to be 1, negative 1, 2. And C is going to be 2, 1, negative 3. Alright. Find the plane equation. So again, these are 3 random points, right? They kind of form a triangle. which we already learned how to find the area of that triangle if we wanted to, but what we need to do is we need to intersect these, and the quickest, easiest way to do that is to turn these into vectors, because AB is already a segment, right? AC is already a segment. But if I turn them into vectors and find the components of those vectors, then I know that I'm intersecting at the origin. So then I know that those two vectors will be contained in the plane that I'm looking for. Right? So I find AB, and again, I'm using A as my initial. You don't have to. You can use B or C, it doesn't matter. Just like with the line problem, we could do whatever we want here. But whatever you pick as your initial, you must keep as your initial. So if I'm going to do AB, I got to do AC. Right? Because I want them to go to the origin here. So 1 minus 5 is negative 4. Negative 1 minus 1 is 0. And 2 minus 4 is negative 2. And then AC. 2 minus 5 is negative 3. 1 minus a minus 1 is 2. And then negative 3 minus 4 is negative 7. Alright, so now I have translated these, right? So I did not change the plane that they were in. I'm just sliding them around. But I moved them to initial point being at the origin now, and I have vector components. So now I've got two vectors that are intersecting in that plane, which is important. So that sort of identifies the plane that they're in. Now, for me to find the plane equation, what am I missing? I need to find my normal, because I don't have it. But what is the normal vector? It's the cross product of those two guys. So now I calculate my normal vector by doing the cross product. So again, we got the second times the third, so that's 0, minus the third times the second. Whoops. So that's negative 4. Sorry. And I got third times the first, so that's 6, minus the first times the third, which is 28. And then we've got first times the second, that's negative 8. Minus second times the first is 0. So my normal vector for this particular plane is going to be 4, negative 22, negative 8. Now, any scalar of n is also a normal vector to the plane. So this is what I would do at this point. Because these are all even numbers, I would just divide them all by 2. So this is twice this, which means they're parallel to each other. So any vector parallel to your normal vector is going to be perpendicular to the same plane and can act as a normal vector. Okay, so my normal vector, and I've got 3 points. Remember how we just did this, right? We had the normal vector and the 3 points. We can go right to our form of our plane equation. Remember, because this is A, B, and C. The question is, what point do we use here? And the answer is, it does not matter. So I've got 2x minus 11y minus 4z plus d is equal to 0. So if I plug in A, I'm going to get 10 plus 11 minus 16. So in this case, D is 21 minus 5. If I use point B, I'm going to get, plugging it in, I'm going to get 2 plus 11 minus 8. 13 minus 5, D is negative 5, right? Because this is 5, so yeah. And if I choose C and plug it in, I'm going to get 4 minus 11 plus 12 plus D. So that is negative 7 plus 12 is 5. Is negative 5. So, again, it doesn't matter which point you pick. So again, what is the process? Given any 3 points, we're going to pick one of the 3 points as my initial, translate it so that they intersect in our plane at the origin, calculate the cross product. That gives me my normal vector. And if you can, reduce it, right? Because, again, if any vector that is a scalar of the normal is also going to be perpendicular to your plane. And go ahead and plug it in to find D. Pretty straightforward stuff. So keep in mind, right, the normal vector is perpendicular to your plane. What does that mean if I've got 2 planes that are parallel, something like this, and what does it mean about these 2 planes? It means they can have the same normal vector, right? Because the normal vector, any line that's perpendicular to a plane is going to be perpendicular to any plane that's parallel to it. Which means if they have the same normal vector, let's say 2x plus 3y plus 4z plus d, right? If they have the same normal vector, in this case 2, 3, 4 is your normal, what causes this thing to slide up and down that normal vector is d, right? That adding that on. So if you see this equation where you have 2x plus 3y plus 4z plus 5 equals 0, and you see 2x plus 3y plus 4z minus 10 equals 0, what do you know about those 2 planes? They are parallel, right? Because they have the same normal vector, but your d values are different. And if your normal vectors are different, then, if you got a normal vector doing this, and maybe a normal vector doing this, then obviously these planes are going to intersect if your normal vectors intersect. And what's cool about this, if your planes are not parallel, right, and your normal vectors are going to intersect, then what does that mean? That means that the angle between the normal vectors is going to be the same as the angle between the planes when they intersect. So if you're looking for a plane intersection, right? So if I give you 2 plane equations, so let's say 2x plus 3y plus 4z plus 10 equals 0, 5x minus 2y plus z minus 11 equals 0. I give you 2 equations for planes, and you want to find the angle between them. What do we do? Well, we just said that the angle between the planes is the angle between their normals. So let's call this plane M, and this can be plane Q. So the normal vector, the normal for plane M, is 2, 3, 4, right? ABC. And the normal for plane Q is 5, negative 2, 1. So now we just have 2 vectors. How do we find the vectors, the angle between 2 vectors? cosine of theta, right? So it's the dot product of the two vectors over the products of their magnitudes. Or in this case, the dot product is 10 minus 6, which is 4, plus 4, which is 8. And then the magnitude here, remember the square root of 4 plus 9 is 13, plus 16 is 29, 25, 29, 30. So, cosine inverse of 8 divided by the square root of 29 times the square root of 30 74.26 degrees. So that would be the acute angle. Now, if, which can happen, you can get a negative dot product, right? So if this ends up being negative, this will never be negative because you're doing square root of the squares. But if this ends up being negative, then if you leave it negative, the theta is going to be an obtuse angle because cosine's negative in quadrant 2. Okay. What would happen? So if this were a negative 8, this then would have been the supplement of what I was looking for. In other words, it would have been 105.74. Right? Not what you want. So to stop that from happening, absolute value around the dot product, and you'll always get the acute angle that's formed between the two planes. So finding the angle between the planes is nothing more than finding the angle between their normal vectors. Okay. Finding the intersection of two planes. Oh, yeah. You guys remember how we did this? So you want to find the line of intersection in parametric form. We're going to go ahead and okay, gang. We've got a couple things left to do. First of all, to find the intersection of two planes. So we found the angle between them by finding the angle between their normal vectors. But to find the intersection of two planes, and we know that that intersection is a line. So back in Chapter 7 we did this, and if you remember, we know that the general solution is what we were looking for, or in other words, find the ordered triple in terms of z. We're going to do the same thing here. So, that being said, I'm going to go ahead and grab example, I'm going to do 50 from the book. So let's say we have 2x plus 4y minus 2z is equal to 1, and negative 3x minus 6y plus 3z is equal to 10. So again, we got two plane equations. And one thing I will tell you is that if we were to take the normal vectors of these two planes and we were to cross them, we would find that the cross product, which is the normal vector, is going to be parallel to the line of intersection. You read that in your notes when you do that, but if you were to take those two normal vectors and cross them with each other, that line of intersection that you're going to find is going to be parallel to those normal vectors. So we're going to go ahead I'm going to go ahead and solve this like we normally would, right? I'm going to solve it so that it's in terms of z. I got two planes. I know their intersection is a line. So I'm going to get rid of my x first. So I'm going to multiply the top equation by 3. And I'm going to multiply the bottom equation by 2. And what's going to happen? Everything cancels out. You get 0 equals 23. So what does that mean? That must mean, because when I multiply the top equation by 3 and the bottom equation by 2, I really multiplied everything by 3/2, right? So this is 3/2 of this, negative 3/2 actually. So this is actually a scalar of that. And what did we find out when that happens? They're parallel. So these planes are, oh, crap, which I didn't expect to happen, but it did, which is okay. So I'm going to go ahead and do another example. I dropped my book on the floor here, so give me a second. Get back to the page. Alright, so these are longer notes. I'm sorry, but they are the last notes, so we're going to live with it. Let's go to chapter 12. Alright, so instead of doing that example, we'll do the previous even example, which is number 48. We got x minus 3y plus z equals negative 2. And we've got 2x plus 5z equals negative 3. Alright, so no y here, which is kind of nice. We can go ahead and just solve for x in terms of z right away. So 2x equals negative 3 minus 5z. So that means x equals negative 3/2 minus 5/2z. So we have x, and we're going to take this and we're going to plug it back in up here. So I've got negative 3/2 minus 5/2z minus 3y plus z is equal to negative 2. And to make my life a little bit easier, I'm going to multiply everything by 2. So negative 3 minus 5z minus 6y plus 2z equals negative 4, because I'm solving for y in terms of z now. So let's see, I'm going to take this to the other side, and I have negative 6y equals, so this becomes a negative 1, and this is negative, so plus 3z. So y is equal to 1/6 minus 1/2 z. So back in chapter 7 we would have said, okay, negative 3/2, I know I did that, minus 5/2 z, 1/6 minus 1/2 z, and z, and then we'd be done. But now we wish to put this into parametric form. So, and the thing that I just told you, remember, is that the normal vectors here, let me just show you this real quick. Because this is x, and this is y, and this is z. Alright? So x equals this, y equals this, and we can just kind of write it out in its parametric form. But I want to show you something. So the normal vector here is 1, negative 3, 1. And I'm going to cross that with the normal vector here, which is 2, 0, 5. And my normal vector then is 2 times 3, which is negative 15, minus 3 times 2, which is 0. And then we have 3 times 1, which is 2, minus 1 times 3, which is 5. And we have 1 times 2, which is 0, minus 2 times 1, which is negative 6. So we have negative 15, negative 3, 6. Now, take a look at the coefficients here, right on the z variable. We've got negative 5 halves, we've got negative 1 half, and we've got 1. So I can think of that as like my slope vector. Remember the parametric form was x equals x1 plus a t, y1 plus bt, etc. So look at this vector and look at the cross product I just got. What would happen if I multiplied each of these by 6? I'm going to get negative 15, negative 3, 6. So what you see is the cross product of the normal vectors of the two planes represent your slope vector. Which means I can use this in my form if I want, or I can just write this out. It doesn't really matter. But writing out what I have now for my line of intersection in parametric form, x equals negative 3 halves, and I can use this, or I can use any scalar of that, right? Because it's all going to be in the same direction as your line of intersection. So for me, I guess making this nice and clean, I would probably divide everything by 3. And I would use this as my slope vector. Minus 5t. Y is 1/6 minus 1t. And z is 0 plus 2t. And that would be the line of intersection in parametric form. So are we really doing anything extra here than we did before? No, because if I would have written this out, I would have x equals 3 halves minus 5 halves, and just swap out the z for the t and be done with it, right? So you have, and then z is equal to t. Is this the exact same equation as this? Yes, because this slope vector is a scalar of this, which again is fine if it's fractions. The only reason I'm telling you this is because when you go to look at your answer in the book, you're going to see this answer here, and you're going to wonder, where did that come from? You know, so since it's a scalar, what you can do is look at the vector that's on z, the coefficients, right? And if I just multiplied everything by 2, I get this answer, right? So you don't really have to cross the normal vectors, but I just wanted to show you the relationship. Okay, 2 more things, and we are done for the year. Woohoo! How do you sketch a graph of a plane given its equation? So let's say I've got 2x plus 3y minus 4z plus 1 equals 0. And if you had a line in standard form, like 2x plus 3y equals 6, the easiest, quickest way to sketch that line would be to use its x and y intercept. So its y-intercept is 2. If I plug 0 in there, its x-intercept is 3. Plot your 2 points, 0, 2, 3, 0, draw your line. Right? That's what I would do. So here, we're going to do the same thing. We're going to find the x, y, and the z-intercept. So the x-intercept happens when y and z are both 0. So it's going to look like this. So if these are both 0, take that to the other side, x is negative 1/2. Your y-intercept happens when x and z are both 0, so you're at negative 1/3. And if I was a smarter man, I would have made that 12, but that's okay. Because 12 is a common multiple of all 3, but no big deal. All right, and then your z-intercept happens when both x and y are 0, so you get 1/4. So again, to sketch this plane, we have -1/2 on the x-axis. We have -1/3 on the y, and we have 1/4 on the z. And then we're just going to draw in that little triangle, and that is a representation of your plane. Pretty straightforward, right? If I'd have made this, if I'd have made this 2x plus 3y minus 4z equals 12, you'd have gotten to see this a little bit better, because your x-intercept would be 6, 0, 0. Your y-intercept would be 0, 4, 0. And your z-intercept would be 0, 0, -3. So you'd have been out 6 on the x, 4 on the y, and -3 on the z, and you'd have had this plane right here. So sketch the 3 points, color in your triangle, and you're good to go. What do we notice about these 2 planes? They are parallel. Okay, last thing, I promise. Find the distance between a point and a line. I'm sorry, not a line, but a plane. It's a big section. That's why we would have done it over 3 days, but that's okay. So, you are given this formula, and this, again, they talk about projections and all that stuff. All you really need to remember is that there's the steps here. You're going to be given a point, and you're going to be given a plane. Right? So let's say P is my point, and it is 1, 3, 5. And then my plane is going to be in the form of an equation, which is, let's say, 2x plus y minus 2z equals 1, whatever. Okay? So you've got your point, you've got your plane, and you want to find the distance from here to here. So the first thing, we know what n is, right? N is the normal vector of the plane. So 2, 1, -2 becomes n. So all we really need to do is find this vector PQ. The question is, what is Q? So Q is another point on the plane. So what's a quick way to find another point on this plane that we've been given? For me, I'm going to use an intercept, because that's quick. And in this case, the y-intercept, because I know that the y-intercept is 0, 1, 0. It doesn't matter which points you use. You can plug in anything you want. But finding an intercept is quick. So that's Q. So then what does this represent? That represents the vector PQ in standard position, which means I need to subtract here. Using P as my initial, that's important. So this is, again, is just some segment. So I got -1, -2, -5. So the idea of a projection, what they're doing here with this dot product, is whenever you talk about distance, you have to measure the distance from the perpendicular, right? So I got to go from the point perpendicular to the plane, right? So that would be its distance. So the only other perpendicular we know of is n. So by using this whole idea, we're projecting this over here, and then we can actually divide out the normal vector length so that we have the actual length of the segment. So that's what's happening here. These are both parallel. Okay, so we've got what we need. We'll just go up and use our formula now. So we're going to take the dot product of P and my normal vector, PQ and my normal vector, which is 2, 1, -2. Divide it by an absolute value because we're talking distance, by the magnitude of the normal vector. The magnitude is 4, plus 1 is 5, plus 4 is 9. So, dot product, negative 2 minus 2 is negative 4, plus 10 is 6, over root 9. And that is the distance between that given point and that plane. So again, what are the steps involved? Get your normal vector. That's quick and easy because we know it's A, B, and C. Find a point on the plane, and again, any intercept will do, X, Y, or Z. Make it easy on yourself. Find PQ, which means we've got to translate to the origin, and then just plug into the formula. And we are good to go. So, being able to find the equation of a line given a point and a slope vector, or 2 points. Being able to find the equation of a plane given a given the normal vector and a point, or just given 3 points. And then being able to find equations of planes for different reasons, knowing when planes are parallel, understanding how to find the distance between a point and a plane, and then also finding the equation of the line of intersection between 2 planes in parametric form. And that is that. So that is the last video lesson for the year. That was an hour and 40 minutes long. I'm very, very sorry. But let me end with this. Did you all hear the joke about the roof? Never mind, it's over your head. Why was the broom late for school? Why did the broom show up late for school? Because he overswept, which is what a lot of you do when you miss our morning meetings. Anyway, I'm done. Good luck. Hopefully, again, I'll see you guys sometime this last meeting this week. If not, have a great, great summer. Mr. Lampkin is out.